Okay, hi everyone, welcome to another session for BitcoinKernel Club, and uh, we will be discussing about Bitcoin kernel. And today we'll be looking at contextual checks. In the previous session, we discussed the context-free checks, how we were able to validate the script, the block, and the transaction as well. And today we'll be looking at all the contextual checks, like how to validate a block fully and how to validate a block header. And you know there will be one more context free check, which is check transaction, which was recently merged in Bitcoin kernel API, CAPI, and it's implemented in the bindings as well. So we'll be looking at that first, and then we'll be going into the contextual checks. Okay, so let's start. So as we have discussed in the previous session, we discussed about context-free checks, and we had this script hex, we have the transaction hex, amount, input index, block header hex, and then we actually wrote a function which would deserialize the script pub key and convert that to pbk script pub key data types, so that we can interact with the Bitcoin kernel. So to interact with Bitcoin kernel, you have to implement the data type to its native format. For example, if the script pub key is in hexadecimal or bytes, then we have to convert that to the data type of Bitcoin kernel, like the script pub key type. As we are doing here, we are converting from bytes. We're converting to bytes, and before that we had the script pub key in hex form, and then we are converting to bytes, and from bytes we are you know converting it to script pub key. After converting, we are also doing the same thing for the transaction, and then later on we are verifying using the like Bitcoin kernel verify script verify API. Yeah. And the next we did was uh, validate the block header. Not validate, actually deserialize the block header. And similarly, we took the block header in hex form, and then we converted that to bytes, and from bytes we converted that to block header type, Bitcoin kernel block header type, and then we passed it to we deserialized and extract out all the fields in block header, that is n bits, block hash, the nonce value, the previous hash of the block, the timestamp the block was mined, and the version of the block. And then we also looked at the context free check for block, that is check block. And note that this is not actually the full validation of the block, but this is actually the pre-validation. What do I mean by pre-validation is that you don't need the whole blockchain state for context free, just the raw block hex value, and then we'll verify it. But if this is invalid or fails for the raw block hex value, then that means the block is invalid. But if the validation succeed, and if it returned true, or basically if it returned valid, then that doesn't mean the block is valid, but it has passed the pre-consensus check, or the first step of the consensus check. To validate fully, we need the block full validation state, or basically full blockchain state, and we'll be looking at that today. Yeah, so we created the block object from the bytes value, and bytes we got from the raw block hex. We converted that bytes using the bytes uh, like a bytes package in Python. And then we also created the consensus parameters, because we need to pass what type of block is this, I mean in which chain this block is in. If it's reg test, if it's mainnet, testnet, or signet. and then we do actually the block check. We call the block check API using the consensus params, and then the block object. And this will return the block validation state. Block validation state is actually an enum which contains three fields, that is valid, invalid, and runtime error. Runtime error means if there is some error in between the checks. For example, there are multiple checks while when the consensus does the validation, and if uh, if one of the check failed, then it will return the runtime error, or basically it will return invalid, or if there is some error while doing the consensus check, then it will return the runtime error. So yeah, the block validation state contains the three enum value, either of the three value, and we'll check whether this validation mode was valid or not. And then after checking if that block is valid, then we deserialize the block hash, the block hash, and the nonce value and the number of transactions in the block. So today we'll be looking at the deserialized transaction, and here since the check transaction was recently being merged in BitcoinKernel C API, it's not actually implemented in the bindings. So very soon we'll be seeing that as well. But for now, we can deserialize the transaction. We'll take the transaction hex as string format, and from hex value we convert that to bytes, and from bytes we convert that to transaction object type, PBK transaction object type. And then we print the transaction ID of the transaction and the lock time, and then we just print the transaction raw transaction value. And then we'll also be looking at the out point. The out point of this transaction. Out point means the previous, or basically the pending transaction. This transaction should spend another transaction, so we'll be looking at that. What is the TX ID of that, and what is the input index? And we'll also be looking at the sequence of this transaction, or basically the input of this transaction. And then we'll be looking at the out points, or basically the outputs. First we'll be looking at inputs, then we'll be looking at outputs. And for outputs, we just want to print out the script pub key or the locking script and the amount that we want to send. So yeah, let's try to run this one. uh, I've already created the virtual environment, installed all py-bitcoinkernel, and you can check that out in the previous session. And now we'll be looking at how we can we'll be running the deserialized transaction code, or how the API deserializes and prints. We'll be looking at that. So Python 3, this is session 8, and okay. Hmm. All right, not sure what this error. I think we need all the transaction data. I guess we need the whole transaction data. Let me delete all this. Let's try to run now. Yeah. So this is actually the transaction data, and then what we are doing is we are actually converting that all whole transaction data to the PBK transaction type, and then printing all the fields in the transaction. So as you can see, um, this is the transaction ID, and what else? And this is the lock time value, and this is the transaction, the representation of the transaction, which just prints the transaction ID, the inputs and the outputs, the number of inputs and outputs. So this is actually the number of inputs. The previous transaction ID is this one for the input index 0, and then this is sequence value, and similarly for the next input we have the previous transaction ID, sequence, and for the third one previous transaction ID and the sequence. And this is the outputs. This is the amount in SAT, and this is the script pub key value. So this is how you deserialize a transaction, and there is also a doc for this one. This is the transaction class in py-bitcoinkernel, and there are lots of methods, and then we have the transaction. Okay, transaction out point basically means uh, the previous transaction that this input is pointing to, and we have the transaction input class which represent the inputs. Similarly, we have transaction output class which represent the outputs of the transaction that we are deserializing. Yeah, so this was it about the deserialized transaction. Now let us move to contextual check. So before moving into contextual check, we need to look at the chain API. So chain API is basically all the blockchain related, the whole blockchain state related class. So first we have the block map, which is actually a dictionary like data structure for reading the blocks from the disk. For example, if you have a data directory, then when we try to read the data directory, we parse that to block map, and then block map contains all the list of the blocks that your data directory has, and then we can look up using that block map object. So yeah, with the contains method, we'll check if a block can be read from the disk. So basically if a block is present in the disk, and then we can also reuse the get item to read a block. For example, you have the block hash, and from the block hash you can just read the block if it's present in your data directory. You don't have to you know fetch the block from your node or from another type, or not another type, but from another data directory where your node is currently running and printing or storing all the block data. If it's present in your data directory that we are actually passing, then it will return. If it's not, then it won't return. And if the reading fails, it returns the runtime error. Likewise, we have lots of class, the block spent output class, which uh, you know which is actually the undo data. Undo data means uh, whenever uh, whenever new block is mined, uh, the mempool state is changed because there are lots of transactions that is in the mempool, and when a new block is mined, uh, the mempool state changes because we need to flush the transaction from mempool and we need to store the transaction to the block. So the mempool state is changed for every block is mined. So uh, the previous mempool is stored in undo data. So for example, if there is a chain reorganization, then we might want to you know uh, get the mempool state from where the reorganization was done, or basically from where the reorganization was done. And for that reason, uh, we store the undo data so that we don't have to create the mempool state again. And we can view that using the block spent outputs class. And similarly, there is block tree map, which is a dictionary like data structure which contains all the entries of the block by hash. This is for just optimization purpose. If you want to retrieve a block, then we can use this block tree entry map. We don't have to iterate all the block and search. That is too much time consuming, and for that reason we have a block tree entry map that stores like uh, all the block with the hash in a dictionary like interface. And block tree entry sequence is another class which is a lazy sequence. And lazy sequence means it's a list, Python list of block tree entry. How many block tree entry are there? So for you know for accessing the block tree entry, for example, if you want to print the block from 10 to 20, then we can use block tree entry sequence, and this will just give the lazy sequence. And this will be helpful when we want to iterate just the blocks that we are interested in. And then we have the chain type, which represent the current chain type, that is mainnet, regtest, signet, testnet, and testnet 4. The chain parameters, which is actually the properties of the Bitcoin network, and that we use to pass to context option. Chain state manager, for example, if you want to create a chain state manager is actually a class which helps us to getting details of the current blockchain state of our node or of our data directory. So chain state manager options is basically, if you want to just see the blocks in regtest, you don't want to see the blocks in mainnet, then we can configure that using chain state manager options. It's you can think of it like a configuration class for chain state manager. Yeah, so we can use set wipe dvs that will just wipe the block tree database from the data directory, and how many worker threads you want to keep. For example, by validation, there are lots of threads that you can configure so that your validation becomes faster. And we can also update the block tree database in memory, and there are lots of configuration methods. And the next is the chain class, which represent uh, the blockchain, whole blockchain state. And the chain state manager, which represents the central manager of the blockchain validation and the data retrieval. Yeah, this is it. And we are interested in process block, which is actually the full validation of the block. And process block, what it does is we need to pass the block, or basically py-bitcoinkernel block object, and it will validate whether this block is valid or not. And this will validate fully, means that we need the whole blockchain state. So before we call the process block, we need the whole blockchain state. And it, here you can see it's return process and validated the passed in block with the change state manager. And processing first does check on the block. If this checks is passed, then it saves it to disk. So whenever we pass or whenever we call a process block, then it does the validation and then it stores the block data to the data directory. And then here we also have the process block header, and process block header is also the full or basically contextual check, and it's not context free. You need the whole blockchain state to also process the block header. We have the consensus params, which denotes the consensus parameters of the chain. Yeah. So this was the API which is related to the whole blockchain and also known as the contextual APIs. So we'll be looking at that. Yeah. So I've already created a Python script for doing all the contextual check. And first we're importing pbk, which is py-bitcoinkernel, and we're also importing temp file. I don't want to store the whole blockchain data in my system, but I want to create a temporary file, read from that file, and when everything is done, then delete that file. And then we also have blocks.txt, which represents all the block data. So I've taken block up to block 206, and then we'll be we'll be seeing all the contextual check using this block data. As I said, we need the whole blockchain state, so it's not possible to you know uh, create the whole blockchain state or basically synchronize the whole blockchain state, but at least we can take up till 206 block. Yeah. So next is the blocks file variable, which is actually the path to the blocks.txt file. And then we have defined another function which is load rectest blocks. So the block data that I've taken is actually the rectest data, and now what it will do is it will take the path of the blocks.txt file, and then it will parse that, and then it will create the pbk.block data type, and it will return the list of the pbk block type, block object basically. So the next is process block header. So we'll process the block header, and processing block header means we are fully validating the block header. Okay. So after we have created the basically we have loaded the rectest block into our basically after we have created the whole blockchain state up till block 206, now we can do all the contextual check. The first check that we are doing is process block header. I've taken three block headers, and we'll see whether this header is valid or not. And then we'll call the process block header API, as we have seen here. Yeah. So we'll call this one, this is inside the chain class, we'll call that, and this shall return the block validation state, and block validation state is, I've already said you, it's a enum which contains the three values: valid, invalid, and runtime error. And we'll also be printing the validation mode. Uh, if you see in the block validation state, uh, and it returns the validation mode. Validation mode contains three enums valued, which is internal error, invalid, and valid. Invalid value is 0, or invalid value is 1, valid is 0, and internal error is 2. Yeah. So let us run this one, and then we'll see what we get. Okay, let us discuss the process block as well, then we'll run the whole file. The next is process block, which contains processing of the block, or basically whole block validation. First, we are checking if the block file exists or not, and it should be true because we have already parsed the block file. And then we are creating a data directory, or not data directory, but a temporary directory where after processing of the blocks, it is stored in the temporary directory. So yeah, as we can see, we are calling the load rectest block, which returns the list of all the PBK block type, or basically block object. And then we have, I've created a connected variable, which is a list of a tuple of block and the block tree entry. And next, callbacks, interface callbacks. If if you know, if there is some runtime error, or if there is some error while we are doing validation, we can check this callbacks. And callbacks is actually returning a value whenever we have failed, or basically whenever we encounter some error while validation. So for that reason we have create callbacks. And the next is the CM variable, which is change state manager, that will load the chain man, or basically the whole change state manager, and it will take the path as the first parameter and the type of the network, and next the callbacks. So if you see in load chainman, so if we don't provide any validation callbacks, then it will just set to none. That means we are not interested in the callbacks. So you can just omit this, but it's actually very much important when we are doing validation, because we might want to see why this validation failed, why this block validation failed. For that reason, callbacks is important, and from callbacks you can just parse why this validation failed, and it will give you the whole log of why this validation has failed. I mean, which validation call this block failed. Yeah. And then we are actually uh, doing a loop, and for each block we are calling the process block, and basically we are processing each and every block from the blocks, which is the list of the PVK block object. And then we are after we have processed all the blocks and we have stored that to temporary directory, now we can do uh, we can deserialize the whole blockchain state. So here we have done the contextual check for the block, and here we are actually retrieving the data of the blockchain state from the temporary data directory. We can call the get active chain. This returns the active chain of the current blockchain state, and then the height of the chain and the number of blocks, it should be 206, and the tip entry, which is basically the current tip of the blockchain state, that should be the block hash of block number 206. And we'll print that tip entry, and we'll print also the best entry. What is the difference between best entry and the tip entry? Best entry means if there is two competing blocking state, then the best entry represents the larger tip of the blockchain state, or basically larger tip of the chain. I mean the larger chain's tip, and we'll see whether that tip entry is the best entry or not. And next, what we are doing is we are doing the ancestor work, or basically from the tip of the blockchain, we are actually going back to 3 or 4 blocks, basically 3 blocks, and we'll be seeing what is the ancestor of block 206, that is 205, and what is the ancestor of 205, that is 204. Next, what we are doing is we are actually reading the block from the disk, and for reading we are just creating a variable that is tip block, and it will return the block data from the chain state manager, and then we'll print the tip block data, like what is the raw block hex of the tip, and whether this hash matches with the tip entry and the tip block, and then we'll also represent that to in bytes format, whether the bytes match or not. We also print that. Now we'll also print the block spent outputs, which is the undo data. And for undo data, we are creating the undo variable, and we are taking from block spent outputs and the sample entry, which is the genesis block undo data. So genesis block has no undo data because that's the first block, and we'll print that undo data, and then we'll also be looking at the coins, or basically the mempool entries of all the undo data. And again we are printing all the block trees by their hash, and we're also printing the validation interface callbacks, whether this block has passed the block check, or whether this block is you know valid or not. I mean whether this block is not duplicate. For example, if you call the process block twice for the same block data, then it will return valid for both of the times. But with validation interface callbacks, you can see that this block is duplicate because this block is already present in our data directory, and we don't need to do the validation check again. So this saves a lot of time whenever we are in a full node and we want to connect to other peers, so that we don't validate the block, the duplicate blocks again and again, because that will utilize a lot of resources, and for that reason we have this validation interface callbacks. So this is the validation interface callbacks. It's a function, and it will return the log for the validation checks. So if block is not found, then we'll just return that block data is not present, or block.txt is not present in the path, in the path provided. So let us run this code. uh, First, as we can see, we have the process block header, and we have returned the validation mode as 0, and that means this block header is actually valid, and the best entry is height 1, because we have just passed one of the blocks, and obviously this one will be the best entry because we have not actually parsed the whole blocks.txt file. So now we have the next is process block, and process block plus chain inspection. And here we can see the chain height after loading all the blocks, which is 206. As we have seen that the whole block data blocks.txt file contains the 206 blocks data. Yeah. uh, so the number of blocks connected and the callbacks fired is 207. And why it is 207? Because whenever we call the validation function process block, it will try to call the next block as well, which is block 207. Or basically it will check whether the 207 block is present or not in the blocks.txt file. If it's not present, then it will not it will return nothing. So that's why the number of connected callbacks fired was 207. And as we can see, this is the tip entry. Basically that this is the height 206 block hash and the data basically. And the next is whether this tip is actually the best entry. Obviously this is the best entry because we have only one blockchain state. So had it been two blockchain state, basically two chains, then this might be different, because tip will actually return the current tip of the blockchain state. Best entry will return the current tip, basically the latest tip from the longest chain. So this might return true or false. Sure. So next is ancestor work. uh, yeah, so here's the ancestor work code. And we are actually looking from height 206, and from height 206 this is the block hash, and the ancestor of height 206 is 205. This is again the block hash for height 205, and similarly for block 204, which is the ancestor of block 205. And the next is we are reading a block back from the disk. After we have processed all the block is stored in the temporary data directory, and then we'll be retrieving from there. So we can read the block from the change state, basically the data directory. And this is the block hash which has the transaction 2 and the hashes match. Obviously hashes match means this block is present in the data directory. And does the bytes match? Yes, the bytes match, because the bytes in the data directory and the the data we are passing matches. And the block spent outputs for the undo data is 0, because as we can that's common sense, because for the genesis block there is no undo data, or basically there was no mempool. For that reason we have the block spent outputs as 0, or basically 0 transactions. And the next is block tree entries by hash. And yeah, so we're getting the genesis entry index from the block tree entries and inside the chain object. And this returned yes, genesis tree entry is found. And we'll check that from the data directory. And then we'll also check all 0 hash present or not. So absent hash is basically we are just removing some of the bytes from the hash, and we'll be checking whether this hash is present or not. So this should obviously return false, because we are actually removing some of the bytes, and we'll be checking whether this hash is present or not. Yeah. um and by hash I mean whether this block hash is present in the data directory or not. And then we have the validation interface callback. And as you can see, it returns checked, which means that this has been checked, or basically this block has been checked, and the validation mode is 0, which means that it's actually a valid block. And similarly, we have another check. This returns this hash is valid, and it returns the mode 0, which represents the valid. Yeah, that was it for the contextual check.